Another common circumstance when we deal with forces is something called an Atwood machine, or some different setups where I would say are similar to Atwood machines. Atwood machine would just be a simple pulley here, which is going to allow two masses which have different weights or different masses to freely rotate. Now, in this case, if we're looking at the individual forces on each mass, we would have the force of gravity. We'll call this on A. We'll call this block A, and we'll call this block B. And then we'd have a tension force here. On B, we would have the force of gravity on B, and then we would have a tension force here as well. Now, if we think about this, if we have zero friction in this pulley, the 20 kilogram mass is going to pull the 10 kilogram mass up, and the entire system is going to rotate in the clockwise direction here. So then if we're looking at these forces specifically, we can say that the gravitational force down on A is bigger than the tension force up on A, and also that the tension force up on B is bigger than the gravitational force down on B. And because if mass B has to accelerate upwards, tension force has to be bigger, and for BA to accelerate downwards, the gravitational force would have to be bigger. Now, because this is tension, we can say that the tension on A is equal to the tension on B. And that's kind of Newton's third law, right? If A pulls down on the rope and B pulls up on the rope, for every action there is an equal and opposite reaction, right? A pulls down and B pulls up. And so, yes, you can think about, well, they're both pointing upwards, but here's how I like to draw Atwood's machines. Let's just draw them and imagine that they're horizontal. Okay, so essentially we're stretching this rope and putting B here, and we're stretching this rope and putting A there. So again, this is going to be mass B, this is going to be mass A. Now, the gravitational force of A would actually be pointing to the right. So this would be the gravitational force of A, and the gravitational force on B would be pointing to the left. And you could think about them as having a little tug of war. And then the tension force on B and the tension force on A. And so now we see this idea of equal and opposite, right? A pulls B, B pulls A. The tension is their equal and opposite reaction. Now what I would do is I would do the sum of my forces. Let's clean that up a little bit. So the sum of the forces, and since I don't have any vertical components, I'm not really going to worry about that. And I can say, okay, let's make the positive direction to the right. So we're going to have the force of gravity on A minus tension plus tension minus the force of gravity on B. And what we'll see is these tensions go away, equals mass total times acceleration. And my mass total here would be the mass of A plus the mass of B, right? Because A can't accelerate without B, B can't accelerate without A, and so they are going to accelerate to the right, but they're going to accelerate at a slower than just if it was just A, because we have this additional mass of B as well. So my equation would look like the force of gravity on A minus the force of gravity on B equals, we'll say mass A plus mass B times acceleration. And this really becomes mass of A times gravity minus mass of B times gravity equals ma plus mb times acceleration. And I can pull out my g here, and it's mass A minus mass B equals mass A plus mass B times acceleration, right? And so what we would see then is acceleration. If I were to solve for acceleration, acceleration equals gravity, mass A minus mass B divided by mass A plus mass B. And so it's going to be some ratio of gravity, right? And again, if we think about this, right, if we cut this cord here, right, if we cut that cord there, mass A would just drop with the acceleration due to gravity. But it's being allowed to drop, but it's being slowed down by gravity pulling the other direction on B. And so that's why we see that our final answer here as acceleration is gravity, but it's going to be smaller than gravity due to this ratio here of the difference of masses divided by the sum of their mass. So that's how I would set up a basic Atwood machine. Now I said there's other ways that you might see this, and another common scenario you'll see is if something's like on a table, right? And you might have an object. We'll call this object A, and there's a rope, and then object B, and we're allowing this system to be pulled off of the table. Well, now if we look at our individual forces, B has the force of gravity down and a tension force up. A has a tension force to the right. It has the force of gravity down on A. It has the normal force on A, and it could or could not have friction. We'll add friction in there, right, for friction. Right? And again, how I would set this up is I'm going to, imagine B is up here and that we're actually just pulling it perfectly horizontal. So I would redraw my scenario as here's A and here's B. Right? So there's A, there's B. And now my forces would look like my force of gravity on B, tension force, those forces are going to cancel out. Force of gravity on A, normal force, and then again, friction may or may not be there. Right? So now I have forces both in the horizontal direction as well as the vertical direction. Setting things up. Sum of the forces in the X, so we'll call that the positive X direction that way. It's going to be the force of gravity on B minus the force, not the force of gravity, minus friction force, right? So in this case, there's friction, and then again, this would be my total mass, right? Because they're connected, it's the total mass that would then be accelerating there. The sum of the forces in the Y would then be the normal force minus the force of gravity on A, and that equals just mass times acceleration. In this case, there's zero acceleration. We would only be accelerating horizontally, not vertically there, right? If we go back to our original picture, this block is not going to jump up or go down. It's just going to be pulled to the right due to this hanging mass there. So that's how I would set that up. And really, anytime, guys, you see that scenario, I've seen something where, you have something that looks like this. This is a pretty complex one, but, you might have a block up here, a block here, a pulley here, and then a rope there. And again, all we're going to do is we're going to imagine this is up here, this is up there, and it would be being pulled perfectly horizontal. Oopsie. But then we would apply those individual forces, right? You'd have force of gravity, you'd have normal force, you'd have tension, you'd have force of gravity, normal force, tension. Tensions are going to go away, and then we'd break gravity into its perpendicular and parallel components, and then I can bring those forces down here and apply them in this scenario here. So that's the best way that I know as how to tackle these types of problems is draw your forces how they are originally, and then now let's imagine it just on a flat surface, and what would those forces look like with my string straight in between both of them. Again, draw the forces as they are originally, and then if it's just a flat string, perfectly horizontal, what are those forces going to look like?